Good evening, everyone, and welcome you all. Today's Applied Thermodynamics Week 1 tutorial, and I am Thananka Sutia, and I will be basically teaching you this course. You already have this theoretical lecture classes, so uh, I will take the weekly tutorial classes, okay, and where we will be solving questions or discussing problems that will be basically helpful for you to understand the what you call the processes, or that will be helpful in solving these assignment questions. So we'll wait for a couple of minutes for others to join, and then in between that, let me share my screen. Yeah, okay, so I think the slide is visible, and okay, so let us begin. So the first thing is that in comes to your mind is like, what is basically thermodynamics? Okay, so thermodynamics is nothing but thermodynamics is the branch of physical science that deals with relations between heat and other forms of energy, such as mechanical, electrical, etc. So what happens basically, in order to understand this, it is just like that. We have lot of physical sciences, so the subject that basically deals with heat and interaction of heat with different other forms of energy is basically what we call, in simple terms, is called thermodynamics. Now the term thermodynamics is if you have studied the part 1 of the thermodynamics, that basic thermodynamics, the term thermodynamics is basically a misnomer. And why is it is a misnomer? It is because like the dynamics is basically it includes motion, but whatever processes basically we study, that is all what we say that it's a reversible process. These are all basically a quasi-static process, and when you are assuming that the process is quasi-static, the term basically thermodynamics becomes a misnomer. But as it goes on, the terminology is continuing. Okay, so nothing to do with that. Now, in order to study thermodynamics, there are various approaches. Like there are two different approaches. One is the macroscopic approach, which we also call as the classical approach in studying thermodynamics. This you also encounter in case of fluid mechanics also. And the another thing is the microscopic approach, which we call as the statistical approach. Now suppose I have now suppose I have a container. Okay, I have a container and I have some gas filled up here. Okay, now I suppose that there are n number of gas molecules. Now if I'm interested in all the individual molecules property, then this basically becomes your statistical approach or microscopic approach. In that case, you have to have a very good grasp of the statistical parameters like mean, standard deviation, and all those things for all, in order to calculate whatever parameters like pressure, temperature, volume, etc. But in classical approach, what we do is that we take an overall estimation. Like say I am telling that the temperature of this box is T. This means that all the parcels, I am assuming that all the molecules are having a constant temperature T over this, so there is no any discrimination between them. So in that case is it is more advantageous for us to study this thermodynamics if we go by macroscopic approach. So in microscopic approach, what happens? Matter is considered to be comprised of large number of molecules, and all the molecules are taken into consideration. And in macroscopic approach, what we basically do is that we consider a certain quantity of matter, certain region of matter, or we can say it's like a global study. That means the entire picture of each and every molecule is given by a global parameter. Okay, now in order to understand these all things, basically this will be basically an introductory class, because we are not permitted to solve your assignment questions. We are just told to give you hint so that you can solve it, and the assignment one is basically a theoretical one. So this will be basically including all whatever you have studied in basic thermodynamics. These all things will be just a quick revision. So if you have studied thermodynamics, or even if you have not studied, you could understand like these are the basic terminologies that we will come across whenever we will be studying this particular subject. So what is a system? So system what happened? Yeah. So what is basically a system? So a system is a quantity or a quantity of matter or region of interest. That means the part which we are focused on. Suppose I am boiling some water, and in this case my concern is this water. So my concern is this water. So the boiling of water, I'm boiling a water in an open container, and my concern is this water. That means I want to study the pressure, temperature, volume change, density change, blah blah blah, whatever change, mass change of this quantity of water. So that means my system becomes my water. Okay, so this is what. Now suppose, now if I am considering that the environment, that whatever is away, this whatever is except water, whatever is surrounding the water, that is my concern. That means I want to study what is the change in temperature due to the due to the boiling of water, what is the change in volume due to the boiling of water, etc etc. In that case, my environment will become my system. So what is a system? System is basically the region of interest or the matter of interest. That means the point of focus where we will be where we will be calculating various changes in various parameters. Okay, now then what is surrounding? So everything external to the system is called surrounding. Okay, so that means we have some region of interest. Apart from that, whatever region of interest is, that is becomes our surrounding. Okay, now next part is next part is universe. Okay, so it is nothing, you combine system and surrounding together. Okay, the system and the surrounding, if you combine together, this is basically your universe. Okay, next is boundary. Now it separates the system and the surrounding. Okay, so basically the system and the surrounding. So in this case, the previous case, just I am taking this previous example, I am boiling some water. So these interface may be considered to be a, this interface of the water may be considered to be a boundary, and if I am taking this as my boundary, so in this case my boundary is basically flexible, because whenever I will be looking at the this one after boiling, so it will be basically decreasing, isn't it? So in this case my boundary is flexible. So what is another conclusion is that my boundary may be fixed. So fixed, like you can say that piston cylinder, or rigid I'm sorry, like rigid container, okay, in this case my boundary is fixed or flexible. So flexible, any flexible example you can say like balloon. Okay, so you are just uh, expanding a balloon, so in that case the boundary is basically flexible. So boundary can be both fixed, and it can be both flexible. Okay, so what are the other things then? Then we need to know what are the different types of system. Okay, so there are basically three types of system: closed system, open system, and the third one is isolated system. Okay, in closed system, what now you come to know that the system and the surrounding, this is what consists of the universe. So what happens there is, in thermodynamics what we basically study is the interaction between the system and the surrounding. Okay, how the system impacts the surrounding, how the surrounding impacts the system. Now the system and the surrounding can interact with each other by means of change of mass, or by means of mass interaction, by means of energy interaction, or both. Okay, now in closed system what happens, only energy interaction between system and surrounding. Okay, so there will be no mass interaction between system and surrounding. And in this case, both energy and mass interaction between system and surrounding. Okay, and in this case neither energy nor mass interaction between system and surrounding. Okay, so what will be an example for this closed system? So closed system, one example, it can be piston cylinder. Okay, so there is like this, a piston is there. So okay, this is one piston, and in this cylinder there are some gas molecules here. Okay, so and in this case you can see that the mass of this will never change because this is a closed container, but the energy interaction with the surrounding can take place. How? By means of some addition of heat or whatever. We will come to know that. Okay, now how is like both energy and mass what you can say is that an example of an open system. One example of an open system is like a fluid flowing through a pipe. Okay, a fluid is flowing through a pipe and you are just considering this as the system. Okay, this is my system. So in this case my surrounding will become, this part will become my surrounding. So now the mass as well as energy interaction is also taking place between the system and the surrounding. Okay, and ideally there is no any example of isolated system, but what in book they says is that a thermos flux. Okay, but let me make you very clear at this point that even the thermos flux cannot give you, even if you buy the most costliest thermos flux of Milton or whatever company or any international company, this thermos flux will not allow you to keep your tea or water or coffee hot for infinite time. This means what? That there is still energy interaction between them, but the comparatively the interaction or the change of temperature will be less. So that's why they give this example thermos flux as an isolated system example, but ideally or practically there is no such isolated system that is possible. Okay, only one isolated system is possible, and that is the universe. And because if you take the entire universe as your system, then there is nothing to exchange, isn't it? So that's why one ideal system or one ideal isolated system will be universe. Okay, now there is another thing like homogeneous and heterogeneous system. Homogeneous and heterogeneous system. Okay, so now what is basically a homogeneous system and what is basically a heterogeneous system? Okay, so in homogeneous system, what happens, the entire system is in single phase. Okay, so you know what is phase. It can be solid, liquid, etc. Okay, and in heterogeneous system, more than one number of phases are present in the system. Okay, so this is an example of heterogeneous system. Now next terminology we need to find is, yes, so this is one thing that you will come more often, and that is thermodynamic equilibrium. Okay, so what is thermodynamic equilibrium? So a system is said to be in thermodynamic equilibrium. Let me write it in Q form: equilibrium with another system or environment thermodynamic equilibrium. A system is said to be in thermodynamic equilibrium if it is in, number one, mechanical equilibrium. That means no unbalanced force. Okay, and secondly, thermal equilibrium, no temperature difference or gradient, and number three, chemical equilibrium, no chemical reaction. So what it means, that if any system A is in thermodynamic equilibrium is another system B, this means that it is in mechanical equilibrium with another system B. That means there is no unbalanced force acting between them. And if it is in thermal equilibrium, like the temperature of the system A is also the same as the temperature of the system B, and it is in chemical equilibrium, that means there is no chemical gradient like diffusion or whatever chemical reaction is taking place between them. Okay. Next is properties. Properties. Okay, so what are basically properties? Properties are characteristic features of a system, or in other case you can say that they are basically the coordinates Okay, you'll understand when I will explain this with a diagram. Okay, next is state of a system. So what is basically state of a system? Condition of a system at a specified time at a specified time uh, defined by thermodynamic properties. Okay, so suppose if this is a PV diagram and this is one point on this diagram. Okay, so this point will have two coordinates. Say this point is point A, so it will be in V1, okay, so this point A, it will have x coordinate V1 and y coordinate P1. Okay, another point there is B, so it is in x coordinate is V2 and y coordinate is P2. Okay, so basically what I am trying to say is that A and B are states and V1, V2, P1, P2, these are basically properties, or basically the coordinates or variable, or simply not all these are basically coordinate points. So what I am trying to say that P and V, these are the properties of the system. Okay, then the next is process. Okay, now from point A to point B, I can go by this part, I can go by this part. This is part 2, this is part 1. So uh, this is called part. Sorry, before process we should actually come to part. Okay, so what is part? A system can change from one state to another state, from one state to another state in various ways. Each of these ways is called a path. Okay, next is process. Okay, now if the path is completely described, that means the path can be written in the form of an equation. It is called process. Okay, fine. Next is cycle. Okay, when a system undergoes a change from its initial state to any intermediate stage and come back to its original state. It is called a thermodynamic cycle. So that means what? Suppose any system starts from this point 1, it went to this point 2 and came back again to this point 1. So in this case your initial and final state is the same. So in this case it is called basically a thermodynamic cycle. Okay, now the next is quasi static process. Quasi static means almost static. Okay, now suppose you want to expand this piston from this point 1 to this point 2. Okay, you want to push this piston from this point 1 to point 2 now. But in doing so, what you will do, at each and every step you will just give a small expansion. That means your, if I am taking this as my y-axis, my delta y will be very 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 small. That means what, how much small you can imagine is smaller than that. Okay, so that means after every time instant you just give a very little or very little delta y expansion. So in that case this type of process is basically, I will call this as my quasi static process. Okay, next we have studied thermodynamic properties. Now there are different types of thermodynamics properties. One is intensive properties and extensive properties. Extensive properties. Now suppose you have a container, okay, and this container's entire mass is m, okay, entire volume is v, and pressure is p and temperature is t. Okay, now this same container you have divided into two half by means of a divider. This is in an equal half. Okay, look, let me draw it properly. Okay, this is divided in equal half. Now the mass of this part will be m by 2 and the mass of this part will also be m by 2. The volume of this part will be v by 2 and the volume of this part will also be v by 2, but my pressure will also be p and my temperature will also be t, and my pressure will also be p and my temperature will also be t of this part. So what this means is that the properties like p and t, they do not depend on the mass of the content, so that's why they are called independent properties. Okay, and the properties like volume and mass, these are basically called extensive properties because they depend on the mass that is present in the system. Okay, that is the mass of the system, that depends basically on the mass of the system. Okay, okay, then next is, we have already given you a hint, like their energy interaction takes place between the system and the surrounding through the boundary. So this energy interaction in thermodynamics is basically done by means of two energy. One is heat energy and another is work energy. So what is heat energy? Okay, it is the form of energy transfer that takes place between system and surrounding by virtue of temperature difference. Okay, work any energy interaction, any energy interaction between system and surrounding that does not involve temperature difference is called work. Okay, so that means what? Suppose this is my system, okay, and this is my surrounding. Now the system and the surrounding has it interacts some energy E, okay, and this energy is by virtue of temperature difference. Okay, then this energy E will be called my heat, which is also called Q. Okay, now there is another energy, there can be another energy transfer E2, which takes not by temperature difference. In that case, this energy is called my work, and which is represented as W. Okay, important thing to notice in heat and work is that both heat and work are part functions. Okay, and both heat and work are boundary phenomenon. Okay, so what do you mean by part function? This means that suppose I want to calculate the work done in going from point 1 to point 2, okay, via this part A, and at the same time I want to calculate from going point 1 to point 2 by the part B. Okay, so what will be the conclusion is that work from 1A to will not be equal to work done from 1B to. So that's why this means that it not only it does not depends on the initial and the final state, it also depends on the part that is followed, and similar is the case for Q1A2 will not be equal to Q1B2. Okay, and that second thing is that both heat and work are boundary phenomenon. This means is that you have to calculate how much heat is crossing the boundary, that's it, or how much work is done at the boundary by the system or on the system. So these are the two things that you need to keep in mind while calculating heat and work. Okay, another thing, sign convention, which is very very important, is that work done by the system is positive and work done on the system is negative. Okay, and for heat added to system is positive. Okay, and heat rejected from system is negative. Okay, So these are the things to be kept in mind. Now we have understood that heat and work interaction takes place between system and surroundings. Now we can move to the laws of thermodynamics, and the first law that we should actually study is from the zeroth law of thermodynamics. Remember, zeroth law of thermodynamics came after the first law of thermodynamics was invented, and the second law of thermodynamics was first and second law of thermodynamics was discovered. The name zeroth law got because it was the only law that involved temperature. You are studying thermodynamics, you are studying the transfer of energy by virtue of temperature difference, and either of these two, the first law and the second law, which you will study after this, does not give any hint of the temperature. Zeroth law is the only law that gives the hint of the temperature. Now first law has already been discovered, it cannot be renamed as the second law, so that's why before 1 the number 0 come. That's why this is called zeroth law of thermodynamics. Remember, don't write this is that zeroth law of thermodynamics is called zeroth law of thermodynamics because it is invented by some scientist zeroth. Okay, so zeroth law of thermodynamics is named zeroth because it came after first and second law, but this is basic of the thermodynamics, so you have to put this law before the first and second law. That's why it is called the zeroth law of thermodynamics. Now what the zeroth law of thermodynamics actually says is that, suppose I have a system A, okay, which is in thermal equilibrium with the system B. Okay, there is another system C which is in thermal equilibrium with the same system B. Okay, so T of A is equals to T of B, and T of B is equals to T of C. Okay, this implies that T of A is of if, and then this implies T of A is also equals to T of C. So that means if a body A is in thermal equilibrium with B and another body C is also in thermal equilibrium with B, then A and C are also in thermal equilibrium with each other. Okay, fine. Now let's go to the first law of thermodynamics. Okay, see, the first law of thermodynamics is basically the conservation of energy. Okay, so the first law of thermodynamics is basically the conservation of energy. So we will first write down the first law for a closed system. Okay, now suppose this is my system and this is my closed system. Okay, so whatever mass is there, it cannot go outside and there will be no mass interaction. This is my system, so there will be only energy interaction between the system and the surrounding. Now suppose my 1 is my initial state and my 2 is my final state, or whatever things I want to show. Okay, so let E1 be the initial energy of the system and my E2 is the final energy of the system. Okay, so now if there is an increase in energy in going from the state 1 to state 2, then my increase in energy E2 minus E1. Okay, this is what my increase in energy E2 minus E1. It should be coming from some heat input and some work done on the system. Okay, so it should be coming by some heat input and some work done on the system. Okay, so why negative? Because work done on the system is negative, so that's why Q minus W is equals to delta U. This is the basic working formula for the first law of thermodynamics. Okay, now in differential form we can write this as dq is equals to dw plus de. Okay, now what is this d means? This is basically inexact differential. differential. Why inexact? Because it is a part function, it does not depend on the points. Okay, dq equals to du plus dw. Now if, remember, this is the basic, this will apply for all. Now if work done is reversible, or we can say PDV, or we can say quasi-static, and such idealistic condition, then my dw I can write as PDV. Okay, then what it basically becomes, dq is equals to dq is equals to de plus pdv. Okay, now if internal energy change is greater than all other energies, then what I can write, dq is equals to du, where u is internal energy, plus pdv. Okay, so this is another simplified form, and this you will deal most in most of your numerical sums. Okay, so this is the first law of thermodynamics for a closed system. Okay, now first law for a cycle. Okay, now in cycle what will happen, same thing, dq equals to dw plus de. Okay, this one we need to do the cyclic integral. Okay, now if we do the cyclic integral, since energy or that internal this energy will become internal energy, and internal energy is conservative property, so this term will basically go to 0. So for a cycle, this dq is basically equals to dw. Okay, so whatever net heat change, it basically goes into net work done. Okay, so this is for a cycle. Now first law for an open system. Okay, suppose in open system, what additional thing will be there, there will be some mass inflow and some mass outflow. Okay, from here mi dot in is coming, and from here mo dot is going out. Okay, and this entire thing I am considering this one as my what you call my this entire thing I am considering this as my this one. Okay, system. So let me, for this one, let me make it simpler. So let me name this one as m1 dot, and this is basically as m2 dot. Okay, so the entry condition was p1 v1, and the exit condition is p2 and v2. Okay, now if there is any increase in this one, okay, so since this is in mi dot rate of change, so there will be e2, what is of e2, e2 of this entire control volume. Okay, e2 of the control volume minus e1 of the control volume, now divided by the time dt. Okay, this will be basically equal to, again there will be some rate of heat input, and there will be some work done by the work done on the control volume, so this will be q dot plus minus w dot. Okay, now now then this will be your Okay, so this one also we can write this one as d e cv by dt. Okay, this terminology we can also write this terminology as dECV by dt. So this is basically my first law of thermodynamics for an open system. Now from open system to closed system, if you want to go for closed system, just this m1 dot is equals to 0 is equals to m2 dot. So these two terms will not be there, so finally you will get the same equation once again. Okay, so having done this, what we can solve, we can try to solve one of these problems, okay, related to the first law of thermodynamics. Okay, so a rigid tank containing air is stirred by a paddle wheel, and the work input input to the paddle wheel is 8000 kilojoule, and the heat released to the surrounding from the tank is 5000 kilojoule. So what will be the increase or decrease in internal energy of the system? What is the external work done by the system considering the air inside the tank as the system? Okay, so what is basically asked, that this is my system. Okay, so here is some air and there is some stirrer attached to it. Okay, now this stirrer, it basically does work of 8000 kilojoule, and in doing so there is some heat release that is equals to 5000 kilojoule. Okay, so now if we apply the first law of thermodynamics, Q equals to W plus delta U. Okay, now they are directly saying that this one is your yeah, so they are directly saying that this is your change in internal energy. So your Q is given to you as, since it is released, so it is given as minus 5000 kilojoule, and this is the work done on the system. Since stirrer does work on the system, sorry, this is yeah, so minus 8000 kilojoule. You just have to put in there, you'll get your answer. So this will be minus 8000 is equals to minus 5000 plus delta U. So your delta U is basically minus 3000 kilojoule. So what it is saying that, oh, I'm sorry, I have just put the opposite values. Okay, so this is minus 5000 and this is minus 8000 plus delta U. So delta U, you will get it, basically get this one as 3000 kilojoule. So what it is basically saying is that there is increase of internal energy by 3000 kilojoule. Okay. Now your next question is that what is the external work done by the system considering the air inside the tank as the system? Okay, so that means the air inside the tank, whatever the air inside the tank is the system, what is the work done by this system? That means what is the work done by the air? Okay, now remember, the question gives you the answer. This is a rigid tank. So if it is a rigid tank, that means the walls are not at all flexible, so the volume or the volume change of the system is not at all possible. So since it is a rigid container, therefore delta V is equals to 0, therefore integration P dV is also equals to 0, therefore net external work done by the system is actually equals to 0. Fine. Okay, let us go to the next question then. A stationary mass of gas is compressed without friction from zero point 0.3 meter cube to 0.15 meter cube at a constant pressure of 0.105 megapascal, and in this process there is a transfer of 37.6 kilojoule of heat from the gas. How much does the internal energy of the gas basically goes changed? Okay, so what it is telling us that, so a stationary mass, this some gas was present here, okay, and say this is a piston arrangement. Okay, now after this is what my initial state 1. Okay, now what is done, it is compressed to the state 2 in such a way. Okay, this is my state 2. So what is telling is that it is compressed by means of constant pressure. P1 is equals to your 0.105 megapascal, and P2 is also your 0.105 megapascal. Okay, and your volume was, initially your volume was 0.3 meter cube, and finally your volume became 0.15 meter cube. Okay, and then in this entire process there is some heat transfer from state 1 to state 2. There is Q1 to 2 is basically minus 37.6 kilojoule. Okay, so from here you have to calculate the work done, your heat is given, and from there you can calculate the change in internal energy. So what is basically your work done? Your work done 1 to 2 will be basically integration of P dV, and since P is constant, this will come out. Okay, you put all the values. So yeah, so W1 to 2 integration P is what, 0, I'm sorry, so this is in megapascal, so that's why this will be basically written in 0.105 into 10 to the power 3, since this is in megapascal, isn't it? And this is your 0.3 to 0.15, okay, dV, isn't it? So this is basically your 0.105 into 10 to the power 3 into 0.15 minus 0.3 kilojoule. So this will give you minus 15.75 kilojoule. Okay, so from the first law of thermodynamics, Q1 to 2 will be equal to W1 to 2 plus delta U, and from here delta U is what, Q1 to 2 minus W1 to 2. What is my Q1 to 2? Is minus 37.6, and this will be minus of 15.75. so finally your answer will be minus 21.85 kilojoule. Okay, fine. Next, in this numericals and all, we will basically be dealing with various thermodynamic processes, and to depict these all processes I will be firstly using the PV diagram, and later on with all whenever we will come to this power plant part, we will basically use other like TS HS diagram. Okay, so PV diagram. Now the first process is isochoric process. So in isochoric process, what happens, your V equals to constant. Okay, so if V is equals to constant, your isochoric process will basically look like this, will basically a vertical line. Okay, so 1, or you can say this is 1, I'm sorry, 1 to 2, this is my isochoric process. Okay, next, what is how do you depict an isobaric process? So isobaric process is nothing but P equals to constant. Okay, so 1 to 3, this is an isobaric process. Now next is your isothermal process. So for isothermal process, PV is equals to constant. Okay, now if PV is equals to constant, we know that this is basically a rectangular hyperbola. Okay, so in that case, my iso, if I want to draw from another point also, I can draw it. Okay, so this will be like, say, I'm sorry, say this is from A to B, so this will be my isothermal process. Okay, now there is one more process called adiabatic process. In adiabatic process, PV to the power gamma is equals to constant, where gamma is equals to 1.44 air. Okay, remember this is this value differs from different ideal gases. So now in this case, PV to the power 1 and PV to the power gamma, where gamma is greater than 1, in that case this will be a much more steeper curve. Okay, this will be a much more steeper curve, say C. Okay, so in this, and polytropic process, if it is greater than 1.4, it will come this side, and if it is lesser, so polytropic is PV to the power n is equals to constant. Okay, so this is your polytropic process. Now what I need to show is that 1 to 2 is isocoric, 1 to 3 isobaric, A to B isothermal, and A to C adiabatic. Now what does this physically mean? Isocoric and isobaric, you could understand that volume remains constant and pressure remains constant. Isothermal is basically T equals to constant. Okay, now how then we got this process is very simple. PV equals to nRT, this is from ideal gas equation. Now if n and r, we know that these are already constant. Now if T is also constant, then PV is equals to constant for this is how it came. Okay, okay, and similarly the adiabatic process also, it came from such formulas. Okay, now we have studied the first law of thermodynamics, we have done numericals related to first law of thermodynamics, but there are certain limitations of the first law of thermodynamics. Okay, so the first limitation is that it does not tell anything about the direction in which there is possibility of energy transfer. Now for example, this is a cup of tea. Okay, cup of tea, and since this is a cup of tea, obviously you will this will be at a higher temperature than that of environment if this is not a cold tea. Okay, so the environment, so this temperature of this is say T and environment is say TE, so T is greater than TE, so that means heat transfer will take place from the cup of tea to the environment. Okay, but the reverse is not possible, we all know that, but the first law of thermodynamics does not tell you. Even if I will give you a question that heat flows from environment to this one, this much amount of heat is flowing from this one to this one, can you calculate the work done, वगैरह, so you could directly calculate, because this formula does not tell anything about us in what direction the heat may flow. Okay, so this is the first limitation of the first law of thermodynamics. Okay, so it does not tell us that whether we are doing the calculation, whether these processes are feasible or not. Okay, whether this is possible in nature, is it possible or not, this energy transfer, is it possible or not, this thing is not being told by the first law of thermodynamics. And secondly, it does not qualify the energies like heat and work into high or low grade energy. Now what does this mean? Now suppose you are rubbing your hands. Okay, That means you are doing some work on your hands. Now you are rubbing your hands and your hands became hotter. Okay, so that means what? You, whatever work you are doing, it is getting converted into heat. Can you do the opposite? Suppose you heat your hand, can your hands be rubbed? No. Okay, so that means all the work can be converted into heat, but all the heat cannot be converted into work. So that means this is what the second law of thermodynamics says us, that basically the heat is a low grade energy and the work is basically a high grade energy, and this is basically told us by the second law of thermodynamics. So the limitations of the first law of thermodynamics is that it does not tell us anything about the direction in which your possibility of energy transfer may occur, and it also does not qualify the energies like heat and work into high and low grade of energy. So that's why the second law of thermodynamics comes into picture. So this is the first, which I have already told you, that how the work is a high grade energy and the work is a low grade, heat is a low grade energy. Now I have told you that if you heat something, the work output will not come. Okay, the work output will not come if you suddenly heat something. So from a heat source, in order to get a work output, suppose you have a heat source here. Okay, this is nothing but a heat source. Okay, you can extract heat from here, you can extract as much as heat from here, but extracting heat will not produce any kind of work until and unless you put some engine here, okay, which will extract heat and will produce some amount of work. Okay, so this is basically what we call as heat engine. Okay, so in order to convert heat into work, you require some machine or some thing, and that thing is basically called a heat engine. Okay, so later on you will come to know that this is also not possible. You will require some sink in order to release some amount of energy to it. So just the beginning. Okay, now suppose you, this is what this is a temperature at Ta and this is a temperature Tb, and Ta is greater than Tb. So basically you are taking heat from a high temperature heat source and you are rejecting heat to a low temperature heat sink, and in doing so you are getting some amount of work W. Okay, now suppose your work is, now you just want to do the opposite. That means you want to reverse the directions of your energy, like you want to take out heat from a cold reservoir and you want to put it into the hot reservoir. So if you want to do, say the same thing, Tb is here and Ta is here, and again my Ta is greater than Tb. Now your purpose is to take heat from here to here. So in that case you will require a work consuming device, okay, which will basically do some work, because some external work will be required, which will do some work to take out heat from this cold body to and dissipate into the hot body. Okay, now such work consuming devices are of two types. Okay, so this will be my work consuming device. It can be of two types. One is my heat pump and my another is my refrigerator. Okay, now what is the difference between a heat pump and a refrigerator? Okay, the difference lies in there. The difference between heat pump and refrigerator lies in their desired output. So by the name of heat pump, you want to heat something. Okay, so just look at this figure once again. Which one is getting heated? The Ta, the source, or that is getting heated, and by how it is getting heated? By delivering Q1 amount of heat to it. Okay, so heat pump desired output is Q1. Why? Because its work is to heat something and it is heating that particular. Now what is the desired output of a refrigerator? And we all know that a refrigerator is basically used to cool something. Okay, now suppose in your home there is some refrigerator and what it is doing, it is basically cooling something. So how it is cooling? It is extracting heat from somebody. Suppose you are keeping an apple in a refrigerator and that apple is being cooled. How it is cooled? It is extracting heat. So in this case, this will be your apple. Okay, that lower temperature body will be apple. Your idea, your entire motive is to keep that apple cool. So that's why you're extracting heat from the apple. So my desired output for the refrigerator is basically Q2. Okay, so this is basically the difference between your heat pump and refrigerator. Okay, the heat pump and the refrigerator is basically differed by such things. Okay, fine. So then let us do some questions related to this. Okay, during a cyclic process, a heat engine absorbs 500 joule of heat from a hot reservoir, does work, and ejects an amount of 300 joule into the surroundings. Okay, now you have to calculate the efficiency of the heat engine. Simple, just draw the diagram of the heat engine. Okay, okay, so this is some TA, this is some TB, and it is taking some heat, it is doing some work, and it is taking Q1 amount of heat, it is extracting Q2 amount of. So but it is telling that it absorbs 500 joule. So your Q1 is given as 500 joule, okay, of heat from a hot reservoir and does and ejects 300 joule. Q2 is basically your 300 joule. Okay, now you have to calculate the efficiency of the heat engine. Okay, so W will be what? If you do the energy balance at this engine, it will be input Q1 is equals to W plus Q2. So basically Q1 minus Q2 is equals to your W. Okay, so this is, then what will be my W? That will be 200 joule. So what is efficiency? Formula for efficiency is nothing but desired output by input. Now what is a desired output for heat engine? The desired output is this W, because your heat engine, your main purpose of the heat engine is to extract some amount of work while taking heat from a high heat reservoir. Okay, so that is my desired output. And what is the input you are taking in that? Your input is basically Q1, because Q1 amount of heat you are taking na, so that Q1 is your input. So your efficiency will be basically 200 divided by 500, and I think this is 0.4. So this is basically a 40% efficient. Okay. Next, a refrigerator has coefficient of performance 3. How much work must be supplied to the refrigerator in order to remove 200 joule of heat from its interior? Okay, similar, but just now the diagram will be opposite, and this will be for a refrigerator. Okay, now it is telling that my COP is equals to 3. Forget what is COP, is just like the efficiency. Okay, so COP is again your desired output by input. Whatever efficiency or something, whatever these things, is basically the desired output by input. Okay, so what is the desired output for a refrigerator? The refrigerator's desired output is Q2. We have already discussed it. And what is the input for a refrigerator? This work done. Work done is the input. Okay, so basically what it is given, Q2 by W is given as 3. Okay, now how much heat must be supplied in order to remove 200 joule of heat from its interior? Okay, so you have to remove how much work must be supplied in order to remove 200 joule. So that means 200 joule have to be removed from here. So this is your 200 joule is given. So that means 66.67 joule. If you have any doubt, you can ask me. Okay, so then let's move on. Now see, these all whatever we are doing, it's fine, but suppose now we all know that every engine has got its or everything has got its limitation. It cannot cross certain limits. Okay, and that certain limit is basically bound by Carnot cycle, Carnot heat engine and Carnot heat pump or Carnot refrigerator. Okay, so what is basically a Carnot cycle? All processes are reversible. Okay, a cycle is made up of a number of processes and all these processes are basically reversible. Okay, so a Carnot cycle basically contains two reversible adiabatic processes and two reversible isothermal processes. Okay, now if you want to draw the PV diagram, okay, so can you tell me which one will be your reversible adiabatic processes and which two will be your reversible isothermal processes? So we know that the slope of isothermal processes are less than the slope of adiabatic process, so 2 to 3 and 4 to 1 will be my reversible adiabatic processes, and 1 to 4, sorry, 1 to 2 and 3 to 4 will be my reversible isothermal. Okay, so here this is basically your heat rejection Q2, and this is basically Q1, and this is your work done. Okay, and this is work input. Okay, so now in the similar thing will be for your heat pump and all, just the direction will be opposite. Okay, now why is it important? That is very very important. Now why is it important? Okay, suppose I have a reservoir at TA and TB and Duns, I'm sorry, W, it's Q1, it's Q2. Okay, and I'm saying that this is a reversible heat engine. Okay, so my efficiency formula will be what? We know this efficiency formula is nothing but desired output by input, and what is my desired output is basically W, and my input is Q1, and this W I can write this one as Q1 minus Q2, and this is Q1, and this is also I can write as 1 minus Q2 by Q1. Now what happens now if this heat engine is reversible? For reversible, or you can say Carnot heat engine, only in that case the Q2 by Q1 can be written as T2 by T1. Remember, this is only possible that the ratio of the heat released or accepted by the reservoir will be equal to the ratio of the temperature of the reservoir. Okay, so this is therefore eta reversible will be equal to 1 minus T2 by T1. So what it is doing, it is basically giving you the maximum possible efficiency. Okay, eta reversible is basically the maximum possible efficiency, and no any engine can have larger efficiency than Carnot engine. Okay, we'll solve one problem and then you'll understand. Okay, an inventor claims to have invented a heat engine that develops thermal efficiency 80% when operating at heat reservoirs of 1000 Kelvin and 300 Kelvin. Evaluate his claim. Okay, what he has claimed? He has claimed that my efficiency is 80%. Okay, and these heat reservoirs TA is given as 1000 Kelvin, and this heat reservoirs TB is given as 300 Kelvin. Okay, now 80% efficiency is given. Now we just have to compare this with the Carnot efficiency, and what we know, the Carnot efficiency is nothing but 1 minus T2 by T1. Okay, 1 minus T2 is 300, T1 is 1000, so that is 700 by 1000, and that is basically 70%. So the highest possible efficiency that is achieved, that can be achieved between these two thermal reservoirs, is basically 70%, and the inventor is claiming it as 80%. So his claim is false. So this is the reason, this is the most important reason for which we need to study this Carnot engine. Okay, fine. Now next is your Clausius inequality. So Clausius inequality, basically it is nothing but the cyclic integral of dq by t is less than or equal to 0. This is the Clausius inequality. Now it is equal to 0 if the process is reversible, process not, if the cycle is reversible, because this is a cyclic integral, and if it is less than 0 if reversible cycle, and if it is an irreversible cycle. Now from this Clausius inequality, what happens, the Clausius, this by means of experiment he have done that if the process is reversible it is basically equal to 0, and the process is irreversible it's equal to 0. So what he has defined, that if any process is reversible, then we can write ds, that is what, entropy change. Entropy change ds can be written as dq by t. Fine. So if the process is reversible, we can write entropy change as dq by t. So that means if we integrate this from state 1 to state 2, state 1 to state 2. Okay, so this is basically, since this is a property, so we can basically write this as s2 minus s1 will be equals to dq by t 1 to 2. Now this we can't do anything. Only thing we can do is that, suppose if it is at constant temperature, then this T will come out and it will be basically the net heat by input. So suppose this, if isothermal, for isothermal, this will be basically S2 minus S1 will be equal to Q1 to 2 by T, where T is the constant temperature. Okay, so this Clausius inequality gave pathway to this particular phenomenon. Now from that Clausius Clausius inequality, we can basically define a thing that is what you call as entropy principle. Okay, and the entropy principle is nothing but entropy of the universe, or entropy of spontaneous processes increase. Irreversible spontaneous process, this all increase. Now what is basically entropy? Entropy is the degree of randomness. Okay, so entropy is basically a degree of randomness, and mathematically if we want to define this as, suppose from 1 to 2 this process is reversible. Okay, and this reversible part is A, and from this part it is basically irreversible. Okay, this is in dotted line, and this is basically my part B. Okay, so from 1 to 2 it went in an irreversible process, and from 2 to 1 it came to in a reversible process. Okay, now from the Clausius inequality, what we can write, dq by t is less than equals to 0. Okay, now I am just putting the entire thing, considering this as reversible or irreversible. I don't know the entire cycle is reversible or irreversible. I am just putting this as this one. Okay, now I can write this one as dq by t 1 to 2 plus dq by t 2 to 1, isn't it? Greater than or equal to 0. Okay, now this 2 to 1 is a reversible process, so 1 to 2 dq by t will be equal plus s1 minus s2 is less than or equals to 0, correct? So from here what I can write is this: s2 minus s1 is basically greater than or equals to dq by t integration 1 to 2. What does it signifies? It basically signifies that the entropy change of a system during an irreversible process is greater than entropy transferred. See, this is my entropy transferred and this is my entropy change, which is greater because this greater than sign holds in case of inequality. So if you want to make it equal, what we can basically write is that dq by t 1 to 2 plus some term generation. Okay, now if this generation term is equals to 0, it is basically a reversible process and it is greater than 0, it's basically an irreversible process. So again, entropy generation is another term which basically tells us that your system is, or your process is reversible or irreversible. Okay, fine. Now we have first law of thermodynamics and we also have second law of thermodynamics. Now can we combine this and form some equations? Okay, so from the first law what we know is that dq is equals to dw plus du. Okay, now for reversible processes, dw is equals to pdv. So what I can write, dq is equals to pdv plus du. Okay, from second law, this is from first law. Okay, from second law what we can write, if it is a reversible process, dq is equals to tds for reversible. Okay, so then what we can write this one as tds is equals to du plus pdv. So this is one equation. Again we know h equals to u plus pv is equals to dh is equals to du plus pdv. Minus plus v dp. Now if it is a constant pressure process, this will be equals to 0. Okay, oh sorry, should not compare this one as now this is basically your tds. Okay, so tds is equals to dh minus vdp. So this is your equation 2. So these two equations are basically known as Gibbs equations, or sometimes this is called as your what you call TDS equations. Okay, now how you calculate entropy? Now this will be see, we will get this calculation of entropy from steam table when we will be dealing with like power plants and all this one, but right now I will be showing you the formulas to calculate entropy change for ideal gas. Okay, so for ideal gas, how we can change from TDS equations, P dV. Okay, so that means ds is equals to du by t plus P dV by t. Okay, now again we know that PV is equals to RT, so that means P dV plus V dP is equals to R dt. Okay, now for constant pressure process this will be equals to 0, so then what we can write this one as ds is equals to du by t plus R dt by t. Okay, again Cv, this can also be written as Cv dt by t is equals to R P dV P by sorry, this is made a mistake here. PV equals to RT, so that means you can write this one as P by T equals to PV equals to RT, so you can write P by T equals to R by V. Okay, so this is P by T equals to R by V dV. Okay, so this is R dV by V. Now if you integrate this, integration ds 1 to 2 Cv dt by T 1 to 2 plus R dV by V 1 to 2, you will basically get this one S2 minus S1 will be equal to Cv ln T2 by T1 plus R ln V2 by V1. Okay, similarly from the another equation, that is T ds is equals to dH minus V dP, we can do this one similar thing, dH by T minus V dP by T. So this will be ds is equals to Cp dt by T minus V by T equals to R by P dP. So this will be after integration S2 minus S1 will be equal to Cp ln T2 by T1 minus R ln P2 by P1. Okay, so we'll do this question now. Air in a closed vessel of fixed volume 0.15 meter cube exerts pressure of 12 bar exerts pressure of 12 bar and at 250 degrees Celsius. If the vessel is cooled so that the pressure falls to 3.5 bar, determine the final temperature, heat transfer and the change in entropy. Okay, so what it is given, you have to just write down first. You are given the pressure P1 is equals to 12 bar. Okay, and the temperature T1 is equals to 250 degrees Celsius, which we will convert into Kelvin later on. Then you are given as pressure P2 is equals to 3.5 bar. Okay, and it is said that the volume V1 is equals to V2 is equals to fixed volume is given as 0.15 meter cube. Okay, so from here we have to calculate the number one final temperature. Okay, so P1 V1 by T1 will be equal to P2 V2 by T2. P1 V1 goes cancel, so your T2 is basically P1 by P2 times I'm sorry. Okay, so your T2 is basically P2 by P1 times T1, and your P2 is 3.5 and this is 12 times T1 is your 250 plus 273. So do you got the answer? It will be around 152.5 Kelvin. Okay, so the next part is determine the heat transfer. So Q is M, since it is a constant volume process, so mcv t2 minus t1 we can write this. Okay, now this is air, so you have to keep in mind some values even if it is not given. So cv for air is equals to 0.718 kilojoule per kg Kelvin, and cp for air is basically 1.001 kilojoule per kg Kelvin. These things you have to keep in mind. These are the values of air. This may not be given in all the questions. Okay, so your mass is given, or is it? No, you have to calculate the mass. How will you calculate the mass? Your volume is given p v by rt, so p1 v1 by rt1. If you do this, you will get it. So 12 into 10 to the power 5 Pascal, and volume is given as 0.15. Okay, and we know the value of R 287, and T1 is again 250 plus 273. Okay, okay, so here you will get, I think this is around 1.18 kg. Okay, so now Q will be equal to 1.18 into 0.718 into what is your T2. T2 is 152.5, and T1 is 250 plus 273. It will basically 523. Okay, so it will be in kilojoule. Minus 392.88 kilojoule. Okay, so the next part is your change in entropy. Okay, so this is a constant volume process. So which formula you will basically use? Delta S, that is S2 minus S1, that will be equal to M Cp ln T2 by T1 minus R Mr ln P2 by P1. Okay, I can also take M common. Cp ln T2 by T1 minus R ln P2 by P1. 1.18, Cp is 1.005 ln 152.5 by 523 minus 0.287 ln 3.5 by 12. Okay, this this will be minus 1.23 minus of minus 0.353, so you'll get it around minus 1.1107 kilojoule per Kelvin. Okay, fine. So next topic is exergy. Okay, now uh, till now, when we have calculated the amount of energy transfer or amount of work done that can be extracted from the system, we have not considered the change with respect to the environment. Okay, because as we all know that all things come in equilibrium, I am sorry, equilibrium with environment, because environment is a large reservoir of anything. Suppose there is a cup of tea, and that cup of tea, even if you keep in whatever furnace you will keep it in, no any insulator is 100% efficient that it can prevent transfer of heat from that particular apparatus to the environment. So in doing so, one state will come at which it will reach the dead state, what we say, or basically it is in thermal equilibrium with that of the environment. So the entire concept of exergy revolves around this. Suppose this is a system, okay, and there are some total energy is present in this part of system, but this total energy could not be converted to another form of energy because environment will play into role. Let's suppose out of this only this much amount of energy we can convert to useful energy. So I can just name this available energy, and this part is basically your unavailable. And why it is unavailable energy? Because environment will play some role in this part of energy. So this available energy is basically the exergy, that is the maximum possible energy that we can take from a particular system is basically is called your exergy. So in other words, exergy is the upper limit on the amount of work a device can deliver without violating laws of thermodynamics. Okay, fine. The next thing is, how do we calculate exergy? So for calculating exergy, it's very simple. So there will be some boundary work, okay, which will be your x work, we can say. That will be nothing but W minus W, work done on the environment or work done by the environment. Okay, in this case the environment variables we will basically P0 or T0, these are basically your environment. So this is my basically, and what this additional term is there is that basically it's your P0 V2 minus V1, where V2 and V1 are the system's final and the initial volume. Okay, so this is what how the basic formula formula works for this one. Okay, now similarly exergy related to kinetic energy is nothing but V square by 2. Exergy related to potential energy is also nothing but G into H. Okay, but exergy related to heat is equals to integration 1 minus T0 by T dq. Why? Because that environment temperature will come into picture. Okay, so that environment temperature does not allow you to extract all the amount of heat into some desirable work. So because of that, the available energy also now, the expression of the available heat energy is also now changed. Okay, fine. Now the exergy due to mass. Okay, the exergy due to mass is basically m into some psi. Okay, and this psi is nothing but h minus h0 minus t0 times s minus s0 plus v square by 2 plus z of z. Okay, these are all derivations are there in books. Okay, you just have to go through, because this will be used in some of the upcoming problems to solve. Okay, and then there are some non-flow and flow processes which also sir have also, I think, have covered in his lecture, so I'm not going to do go details in this. So quickly go through the last topic of today's talk, that is basically your exergy principle and exergy destruction. Okay, so what is basically we have learned the entropy principle is just like the opposite of that. Just like the entropy of the universe tends to increase, the exergy basically tends to decrease. Okay, and this exergy principle basically it tells us that for reversible process, exergy destroyed is equals to 0. For irreversible process, exergy destroyed is greater than 0, and for impossible process, the exergy destroyed is less than 0. Okay, now with this I will basically conclude today's class, because a bit too theoretical it's today, so can't move on much, because we are not allowed to solve questions if it is not at all discussed here. So okay, and other things we will cover in the next class. So yeah, with this I will possibly conclude today's class. Thank you very much for listening.
Thank you, sir.
Yeah, thank you.